Welcome back, everyone. Let's talk about the test. Specifically, derivation 4 on the test, which was fundamentally broken. And I want to offer you my very sincere apologies for that. This is my nightmare, where I give you a problem that's not just difficult, but actually impossible to solve. So really, really sorry about that. The best bad solution that I can think of is to give everybody full marks on derivation 4. That is not optimal. Let me acknowledge that that is not optimal. It's definitely a less than perfect solution, but it's the best one I could think of. So we'll go ahead and do that. Sorry. So a student got in touch, was concerned that I would therefore, this solution had the negative result that I would therefore make the exam harder to compensate for the bump in the mark, and I want to assure you that I am not going to do that. I am not going to do that. For one thing, I won't have the results from your test back for about 2 weeks, and I have to hand in the exam on Friday this week. So there can be no influence of the results from this test on the exam. And I don't predict that. I think this is a bad enough situation for you as students that I don't actually predict that the average will be markedly higher, even having given everybody. So it will bump the students who would have done the poorest on this. So if you were going to write nothing on the derivation 4, you'll still get the marks. But I don't think that it's better for you in any way to have this solution. So I'm not making the exam harder for sure. Any questions about this, or angry comments I would also accept? I really had that white hot sting of failure, let me tell you. It was a really bad situation. I feel really, really bad about it. But we're here now. The problem was one quantifier. It was one existential that should have been a universal. There was that typo, and that was it. Okay, so if there's no questions about that, I'd actually like to take the opportunity to just jump ahead a little bit and show you how I and the TAs figured out that this was a fundamentally broken derivation. So I'm going to now prove to you beyond a shadow of a doubt that I really screwed up. So here we go. I'm going to do what's called a, so here's the derivation. So here is the evil derivation that many of you slaved away at, fruitlessly trying to get a solution to. And what I'm going to do is prove to you, using what's called the invalidities technique, that this is an unsolvable derivation. Not just that it's hard, but it's literally unsolvable. So let's do that real quick before we jump into the multiplace stuff. We're going to do that. I'm just going to breeze over this as a kind of preview. We'll do this more intensively once we're done, once we're at the end of the course. So the last couple of classes will be this stuff where I'll do this in depth. So you don't have to understand this deeply now, but I just thought I'd demonstrate it. Because you might be wondering, a number of students got in touch asking like, hey, how do you know that this thing was unsolvable rather than just hard? And here's how. Okay, so recall our definition of validity. That is, it's valid if there's no possible scenario in which the premises are true and the conclusion is false. So here's how you prove that an argument is invalid. You find a scenario where the premises are true and the conclusion is false. So here's what we're going to do. We're going to say, this has got to come out as true, this has got to come out as true, and this has got to come out as false. Now, in sentential logic, that was a bit easier to do because we just had true or false atomics. Here, we have to kind of imagine a universe in which this is happening. I'll be able to show this to you if we imagine a universe of just 2 objects. So given 2 objects, we'll call them object A and object B. If I can find a way of assigning truth values to the various atomics. So does B have the property A? Does B have the property B? Does D have A? Or sorry, does A have the property B? Does B have the property B? Does A have the property D? Does A have the property, or does B have the property D? Sorry. And so on. So these are all the possible assignments. HB, FA, FB. Okay, so given those 2 objects, if we can, and so you can see these are all of the possible ways, so these are all of the possible combinations of objects and predicates. And then if we can find a way of assigning truth values, either true or false, to each of these, where the premises come out as true and the conclusion comes out as false, then we'll have proven that the argument is invalid. This is called the invalidities method. Okay, so I'm just going to zip over this. We'll talk more about how to find these things when we get to it, but just to show you. So we'll start from premise 2 here. You can make premise 2 true just in case there's at least one of these two objects. There exists at something such that it's got both the property B and the property F. So let's just choose A. We'll say that A has the property B, so BA is true. Is that clear? So I'm saying the object, these are objects, and these are all our properties, of course. The object A has the property B, and that same object has the property F. Make that true, all right? That makes premise 2 true. So far, so good? Okay. So just for the sake of brevity, I'm going to go ahead and say, let's just assume that all of, so this has got to, okay, actually, let's deal with the conclusion. So this has got to be false. This major connective has to be false, which means this thing has to be true, and this thing has to be false, right? The only circumstances under which something is conditional turns out false. So it's got to be false that there's any of these two objects that has both the property F and the property D. So far, A has got the property F. We've got to make sure that A does not have the property D. So we've got to make sure that's false. So there, we made that false. And we've got to make sure, for example, that B also doesn't. So we'll make both of these false. Okay. Okay. Now, make this true. So this says for any object, for both A and B, if that has the property B, then it doesn't have the property H. So A has the property B. Let's make sure it doesn't have the property H by making this false. Okay? And then if we make this false, we've trivially made this true, right? Because this doesn't have the property, B doesn't have the property B. Therefore, this thing comes out as true. Okay, so now the conclusion comes out as false. Now let's check this one. How do we make this one true? Well, let's see what we've got here. So there exists an X such that, and at least one student was concerned about this conditional inside an existential. I mean, it's a fine, there's nothing logically wrong with that. It's just a weird sentence. It's a weird sentence because it comes out as true just in case anything fails to have the property B. So long as there exists anything that fails to have the property B, this conditional comes out as true. This fails to have the property B, so this must be true, which means this has got to be true as well. In order for this conditional to come out as true, because the consequent is true, then that means that this has to be true as well. So there exists at least one object that has the property B and doesn't have the property D. Well, this has the property B, A does, and A does not have the property D. We'll just fill this in with false, and we're done. Okay. If that wasn't super clear, don't worry about it for now. But what I just showed you, what we've ended up with here is an assignment of truth values to all of the possible atomics given our two objects. And in this assignment of truth values, the premises are all true and the conclusion is false. And recall that a derivation is a proof that you can never be in that situation. So if you've done the derivation properly and started from, of course, a valid argument, because why wouldn't you start from a valid argument? Who would do that to you? You're proving that it's impossible for the premises to be true and the conclusion is false. And I've just shown you that this argument, there is at least one possible situation where the premises are true and the conclusion is false. Therefore, derivation 4 was in principle unsolvable. QED. Okay. So there's that. Again, my sincere apologies for that. It is my fault. And yeah. So we're going to have a better error correction process for the exam, I assure you. We're going to take extra steps above what I was planning on taking on making sure that all of the derivations are solvable, all of the symbolizations make sense, and so on. Okay? Okay, any further comments or questions on this? Yeah?
Symbolization questions seemed stylistically very different from what was in Logic 2010.
Yeah, yeah.
How do we compare in the future?
So the question, if you're listening from home, the symbolization questions are very different, and that's true. I hope that they were solvable given the skills that I taught you. That was the goal. That's always the goal. Some of them were genuinely tricky. Some of them were genuinely hard and would have been challenging to solve given the things that I've talked to you about. But if I make, basically, if I don't intentionally put some challenging questions in here, the average for this class will be so high that the department will be forced to curve it, basically. So that's the danger that I'm fighting against, of having just everybody gets 99 on the thing. And that's what, if I made it just exactly like what I showed you in class and on Logic 2010, that's basically what would happen. So I don't love the situation, but that's the situation we're all in.
Yeah, it wasn't really the level of difficulty, it was just the way they were worded. It seemed boring.
Okay, okay. I accept your comment, and I will.
I did a lot of practice problems.
Yeah. I will attempt to make the exam less weird in that way. I would like the questions to be challenging but not weird, if that makes sense. So I will edit the exam with that in mind. Yeah? Yeah. Okay. Any others? Yeah. So it was supposed to be, this was supposed to be the universal, I believe. And some people very cleverly, just immediately after the exam, inferred that this was unsolvable, not from having done this, but from having just looked at the fact that the premises were all existentials and kind of intuited that this was going to be a problem. Yeah. It's very rare that more than one person comes up to me after the exam and says they think there's a problem, and there's not a problem. So I went home in quite a panic. Yeah. Not that I am sympathetic for your plight, not the other way around, but anyway. Okay. All set with this? Yeah.
How question in the symbolization part. So there is a question about like unlike the, so
Yeah.
how to symbolize. Is that negation of all the other people?
You could do it that way. Yeah, so we're accepting a bunch of different ways of doing that. Yeah. Okay. Okay, let's get to new content. Okay. New stuff. So there's going to be an exercise. It's not due this Saturday. Please note, not due this Saturday. It's due next Tuesday. Sorry, it's not due this Saturday. It's due next Tuesday to kind of give you enough time. It's the shorter one. It's half as long as the exercises you're used to. There's 5 questions, 5 symbolization questions, and we'll do everything that you need to know to solve these today. That's the plan. Okay. Okay with that? Right. Okay, so let's move on to multi-place predicate logic. So we're adding the final wrinkle to our symbolization and derivation skills. Like I said, we'll have 2 more small things to learn at the very end, which are invalidities, which I just showed you, and something called expansions, which helps make the invalidities easier to solve. But this is basically it, the last wrinkle that you'll have to learn. So far, we've had no way to express relations between things. For example, Yao Ming is taller than SHAQ. That's a relation between 2 objects, isn't it? Perfectly normal relation that you're used to. In sentential logic, this is all we would have been able to say about it. We would have to symbolize it something like T as the predicate is taller than SHAQ, which is a pretty weird predicate, and doesn't really get the deep structure of what that sentence is saying, because it's not just giving you a predicate, it's giving you a relation between 2 objects. So that's kind of unsatisfying as a complete system of logic. So what we'd like, rather, is to do the following. we want to introduce two-place predicates, predicates that take two objects. So now we've got a couple things to notice here. T2, so here's how I'm going to show you multi-place predicates. There's going to be a T in either a superscript 1 or 2 or 3 to tell you the number of places. And it says A is taller than B. The object A is taller than the object B. So this is the taller than relation. And then we can represent this as a relation between two objects, not just a weird predicate where we shoehorn in somebody's name. Notice also that we're going to put these two-place predicates, multi-place predicates, in brackets. So we've never done brackets before like this. Yeah. Yeah. Sorry. Order matters a lot. Let me show you an example. Notice the heart-rending difference between these two sentences. John loves Amy, and Amy loves John. Movies and TV would be much less exciting if those were logically equivalent sentences, but they are not, of course. So the way that you're going to determine the order of the predicates is given by, so L says A loves B, and then the order in which they be symbolized matches the order that they appear in that sentence. So L bracket JA says John goes in the A slot, and Amy goes in the B slot, or vice versa. So order matters a lot here. Order matters. Order tells you which thing stands in the relation to which other thing, or which part of the relation they stand in. Yeah? Okay. Notice also, I think I said this a minute ago, notice the brackets. So before, the thing on the left there is wrong. The single place predicates, we have not been putting brackets around the object. I would like you to continue to do that. Continue not to put brackets around single place predicates. But with multi-place predicates, we want these brackets. So do use them for multi-place predicates. Yeah? Just, this is the stylistic convention. Okay. And you're going to have to remember this. One of the reasons I'm going to require it on the exam and why I'm going to be doing it in class is because Logic 2010 requires it. It wants you to do these brackets when you're doing symbolizations, when you're inputting the atomics, which, by the way, this is now, we've got a new definition of an atomic, because it's you can have a multi-place atomic here. So when you're inputting the atomics for your symbolization questions, you need to put in the brackets or it will tell you it doesn't know what you're talking about. Yeah. Okay. Okay. So we're really just doing the kind of the super basics of it right now. But we can go to three-place predicates. I think 3 is the most that I'll ever give you. I'm not going to give you a 4, 5, 10-place predicate. There's nothing logically wrong with that. You can have as many places as you want, but 3 is enough, right? That's plenty to deal with. So 3-place predicates, you deal with these things all the time. There's nothing kind of bizarre or mind-bending about this. For example, Corey was taught philosophy by Vincent. So if we want to say A was taught B by C, is a 3-place relation, a relation between two people and a subject matter. And we would symbolize that as A, Corey, was taught B, E, philosophy, by Vincent, F. Yeah? So far, so good? Yeah.
Letters between A or A onwards, does that mean that each instance is like considered a name?
Yeah, well, I mean, so you can have these between, so you can have multi-place predicates with variables in them, for sure. But each of those are, because they're before I, those are considered names. Yeah, yeah. So it's a relation between 3 names in this case. But we could have done X, Y, and Z in there, and it would have been a relation between 3 variables. So if you're doing this quantified, which we'll do with quantified sentences in multiplace. Anybody else? Okay. Just another quick example, just to show you that you deal with these 3-place predicates all the time. There's nothing uncommon about this stuff. Ontario is between Quebec and Manitoba. So betweenness, something is between something and something else. problem there, right? And again, the order in which you put them into the predicate is the order in which they appear in the symbolization scheme. So the order in the symbolization scheme tells you which order you plug them into the multi-place predicate. So how would you symbolize this? We'd say B, obviously, B brackets. That's the only predicate I've given you. And then something is between something and something. So G is Ontario, is between E and F. Ta-da. Yeah?
Because you put Quebec first in like the sentence, shouldn't it be GFE? Or does it even matter if it's between?
Yeah, in this particular case, because betweenness is transitive between the two things that you're between, it doesn't matter. But yeah, yeah. It's a good catch though. Okay, you okay? Okay, let's roll on. Okay, now let's add some layers to this. So now let's add quantifiers in, which does add some substantial complications to this picture. So up until now, we have not really thought hard or worried about which order our quantifiers are in. Now we have to think about that. We have to think about what's got broad scope, we'll say, and narrow scope. And here's why. It's going to make the difference between saying a particular thing or a generic or random or whatever thing. So here's a sentence that's ambiguous. The first sentence has two possible readings, which are quite different. They're two different meanings that are reasonable to infer from this. Someone has been everywhere in the world. Okay, that could mean either of the following two things. There's some person who's been literally everywhere. They're busy, they've been around. Or for every place in the world, at least one person has been there, but it doesn't have to be the same person. Do we agree that those are both kind of valid readings of that first sentence, the top sentence? It's not clear which of those is meant. And hooray for logic, we're going to give you the tools now to disambiguate what those two different meanings are and say clearly what the two different readings are. Okay, so there's going to be a difference in the way we symbolize those two different readings of this ambiguous sentence. Okay, so first let's do some specific person has been everywhere in the world. So if we want to say a specific thing, there exists a specific person, we give the existential quantifier wide scope. So to see how there's a universal buried inside the existential? So by giving the fact that the existential is the big one that has got the universal inside of it is how we symbolize that there exists at least one thing such that it's a person, and for everybody everywhere in the world, they've been to that place. So this is the reading where we say there's at least one human who's been everywhere in the world. Okay. Now let's contrast that with the other reading, where instead of the existential getting wide scope, the universal gets wide scope. So now we're saying for all of the places in the world, there exists at least one person who's been to that place. Okay. Exactly why there's the difference in the symbolization will become much clearer when we do expansions at the end of the course. Essentially, the answer is the reason why these two are different, very briefly, is that ultimately an existential is a series of or statements. So you will translate existential sentences into a long series of disjunctions. An existential says, well, either this guy has been everywhere in the world, or this person, or that girl, or them, or them. It's a long connected series of or statements. And inside each of those or statements is the universal. So either Billy's been everywhere in the world, or Tom's been everywhere in the world, or Sally's been everywhere in the world, and on and on and on. Okay? So the existential gets expanded into a series of disjunctions. The universal gets expanded into a series of conjunctions and statements. So for every place in the world, such that, so for every single place in the world, it has to be the case that there exists at least some random person who's been there. And that's a series of and statements, not a series of or statements. So what would make this true is very different than what would make the existential being outside true. The existential is being made true by there being just one person who satisfies the criteria. This is made true by every single place in the world having this property of there exists some random person who's been there. Okay, if that explanation wasn't satisfying, please feel free to just memorize this as a convention. So as a convention, we're going to take this up. So we talk about this in terms of wide and narrow scope. The quantifier that has scope over the whole sentence has got wide scope. And as a convention, we're just going to say, I mean, there's logical reasons for this, but just take it on board as a convention. If you've got a mix of existentials and universals, if the existential has wide scope, then we're talking about a specific thing has this property such that all things. And if the universal has wide scope, then we're saying everything has this property such that there's this generic thing. Okay, let's do this again. More examples to kind of give you opportunities to latch onto this. So, some dogs sniffed every tree. Once again, it's an ambiguous sentence. It's unclear what that means. It could be some specific dog who's an extremely prolific sniffer, has gone all around the world and sniffed all of the trees. Or each dog has been sniffed by at least one dog, but they don't have to be the same dog. It's not that the same dog went all around the world. It's just that there's at least one dog that has sniffed them. Okay, so the way to represent the difference here is to give, in the first case, the existential wide scope, and in the second case, the universal. So here's what that looks like. For D is a dog, A is a tree, and B, A was sniffed by B. So there exists at least one thing, that's the main claim being made by the first symbolic sentence there. The main claim, the major operator of that sentence is an existential, is that there exists at least one thing that has the following properties. It's a dog, and they've sniffed every tree. The main claim being made by the second symbolic sentence is a universal. It's saying, for everything in the universe that's a tree, there exists some generic dog that sniffed it. So it goes from being specific in the first one, a specific dog, to a generic dog in the second one. Okay? Okay. So when you're symbolizing things, there's some indicators, some parts of the sentence that disambiguate. So you can make the sentence non-ambiguous by saying stuff like this. So if you say some specific dog, that's clearly not saying, so if you say some specific dog sniffed every tree, I'm clearly not saying that I'm not talking about the set of all dogs, right? I'm talking about one specific dog. A certain dog sniffed every tree, or the same dog sniffed every tree. These are scope indicators that help you disambiguate what gets wide scope and what gets narrow scope. All of these add up to the existential getting wide scope. Because we're talking about there exists some X such that X is a dog. And we're only claiming that there's one of these things, right? We're only claiming that there's one dog that meets the following criteria. That's what the existential does. Okay, so keep an eye out for these scope indicators. The opposite, when you're indicating that the dog takes narrow scope, there's fewer of these that I could think of. Some generic dog is the standard one, or some random dog, I guess is the one I've been saying out loud. So generic or random, these indicate the scope of the relative scope of the universal and the existentials that are involved. You really only get this ambiguity when it's a mix of existentials and universals, which is why I'm talking about which one of those two is outside. If it's just universals, then it's just universal. And if it's just existential, then you're just talking about specific things. So this is only an issue where there's a mix of universal and existential, and these are the indicators that you can give to disambiguate the scope, the relative scope of the existential and the universal. Okay. So, propose to just jump into a couple of examples now. We'll spend the rest of the time just doing examples, unless there's questions before we do that. Questions about any of this stuff? Okay. So, talk really quickly about strategy, and then we'll jump into examples. So, and I'll also, hopefully by the end, I want to show you a couple on Logic 2010 just to make absolutely sure that you know the commands or whatever. It's very, very similar. In multi-place symbolizations, I strongly recommend that you start by assigning variables to the multi-place predicate. And that just helps you just start with the multi-place predicate, sort out how it's going to be, and then you use what you did there to figure out how to assign variables to all of the other predicates. So let me show you that in practice to make it concrete, yeah? Okay. Oops. Okay. So, a certain dog, we got a scope indicator to tell us that we're talking about a specific dog. A certain dog chased every cat in the neighborhood. Okay. So here's my strategy hint. What we're going to start with is the multi-place predicate, which is E. And we're just going to decide for ourselves which variables are going to go in which slot. So we've got this slot and this slot. So I'm just going to say E, X, Y. Okay. So we know now, having made that determination, something is going to chase something. Now, what chases what? Well, the dog is chasing the cats, right? That means that X is going to end up being a dog, and Y is going to end up being a cat. Regardless of how the quantifiers are ordered, just having made that decision, which variables go in which parts of the multi-place predicate, we can work backwards from there and decide which predicates to apply to those variables. Yeah? Okay, so having decided that, now we can deal with the rest of the sentence. So, a certain dog chased every cat in the neighborhood. This is the certain part, the word certain is a scope indicator. It indicates that the existential takes wide scope. Right? So we're talking about a specific dog that chased every cat in the neighborhood. So let's say there exists an X, because we decided that X was going to be our dog. There exists an X such that, first off, it's a dog, and now we can deal with every cat in the neighborhood. Now we've decided every cat is clearly universal. We've decided that Y is going to be our cat's variables. So we say for all Y, if it's a cat and if it's in the neighborhood, then we just plug in this thing, E, X, Y. Oh, that's two X's. Clearly, those are two X's. Bracket, bracket, bracket. 1, 2, 3 brackets on this side. 1, 2, 3 brackets on that side. Okay. Hooray. Okay, so now we've symbolized the idea that there is some certain dog, a specific dog, at least one dog, that chased for all of the cats that are in the neighborhood, that specific dog chased that generic cat. We did that by giving the existential wide scope, the universal narrow scope. Any questions? Yeah.
The X that is inside the innermost universal scope, as we typically learn, doesn't that mean that it's technically a different object of the existential?
No, you're right to worry about this, but in this case, it's not right. So if I'd made, here's why you have to make the different. So when we made these decisions, you got to make these two different things. If you want them to be a cat and a dog, they have to be different. If this had been X, then this inner quantifier would have bound to this x. And then we would have that problem. But because, so this is still, notice that the scope of this quantifier is this whole sentence. So this x here that exists in our multiplace still is bound to their existent x. So we know that what this is claiming is there's some object that satisfies this predicate, and for everything in the neighborhood, it satisfies this predicate as well. So it's the same object in each x here, because nothing has overridden its being bound to that existential out in front. Okay. So it does matter a lot that you make sure that these are different variables, so that we don't get the inner quantifier taking over and binding to the multiplace predicates x there. But so long as you do that, this is good. This is, yeah. So just because I've started a new quantifier doesn't mean that the scope of this quantifier out front stops. It's still, this x is still bound to this. Any other questions? Okay, I propose to do the same question, but with the opposite sort of scope. Okay, so we'll just go through this again, maybe slightly faster because we just did it. Once again, start from the multiplace predicate. Start from the multiplace predicate. We're going to say E, X, Y. And it's still the case that it's the dogs chasing the cats. A chased B. It's still going to be the case that X is our dog and Y is our cat, right? It's not cats chasing dogs, it's dogs chasing cats in this sentence. Okay. Now, I indicated to you that this has got the reverse scope of the last sentence, right? So it's not going to be the existential out front, it's going to be the universal. So for all, but we still want to make it Y. So we still want to say for all of the cats. Yeah? Because we're saying every cat. So for all of the things such that it's a cat and it's in the neighborhood, the following holds true. That has been chased by some dog or other. That's where I'm trying to indicate to you that it's a generic dog. There exists at least one thing, now we're going to use the dog variable, such that it's a dog, and it chased that cat. Bracket. Bracket. And how's that? Reasonably satisfied with that? Yeah. So that's me trying, so the question is, what do you mean some dog or other? That's me trying to indicate that it's not a specific dog. So I could have said there, instead of some dog or other, some generic dog, or some random dog. So what I'm trying to indicate is that there's not one dog that chased every cat in this circumstance. It's just that for every cat, there's at least one dog out there who's chased them. Yeah? Okay. Further questions, or we'll do one more example, and then I want to show you Logic 2010 doing this stuff. Okay. One more example. You can fool some of the people all of the time. This sentence is true. Okay. Okay, so it's pretty clear, hopefully. Well, actually, this is ambiguous, isn't it? This is ambiguous. It could mean a couple of things. It could mean there are a few people out there that you can fool all of the time. So there's a couple of specific individuals that at any time of the day or night you can fool that individual. Or it could mean for any given time and find at least one person that you can fool. Maybe there's nobody you can fool all of the time. There's no specific person that any time of the day or night they can be fooled. But at any given time, you find at least one person that you can fool. So this is an ambiguous sentence. OK, let's do one version of it. So let's say you can fool some specific people all of the time. Let's make it the person is the specific thing. Once again, let's start with our multi-place predicate. So f, x, y, that makes you can fool A, this person, and then y is going to be a time. Oh. OK. So in this case, we're saying there exists some specific person, gx, and for all of the times, actually we don't even need that. For all times, you can fool them. F, x, y. Is that right? No. That's not right. Sorry. I had to add that it's a time for all y. If it's a time, and that was going to be a free variable, so that would have been terrible. All right, so now f(x, y). 2, 3, 2, 3. OK. So there exists at least one person such that for all of the times, for all objects such that they are times, you can fool that person at that time. Yeah? OK, let's do it the other way. So suppose instead of saying specific person, we just said all of the time you can fool at least one person. So let's rephrase this in a non-ambiguous way. At all times, there's at least one person you can fool. So let's symbolize that. So once again, I'm going to stick with this way of deciding how we're going to assign our variables. So for all y, if it's a time, then there exists at least one person, and you can fool them at that time. Yeah? OK. Quick questions? OK. In that case, let me just show you this really quick on Logic 2010. OK. So, I mean, hopefully it should be fairly clear from what we've done before, but just to remind you of one little thing. Everyone loves someone. Once again, it's ambiguous. It's ambiguous. So here's one way of doing it. We'll make it a universal. We're saying a conditional. And if something is a person, for all x, if it's a person, then the existential, then there exists some y such that, make it a conjunction. Once again, that they need to be a person, gy, and, OK, this is basically the thing I wanted to show you. Oh, no, the gy can't possibly be right. Atomic fy. So now we've got two different people here, right? We've got for all persons, there exists at least one random person such that the first person loves them. G, and you got to use the brackets, xy. Did I do that right? Hooray, I did. Yeah? OK, if I hadn't put the brackets in here, this would not have worked. So if I just said gxy, it could not, it doesn't, it pretends it's never met me before, doesn't know what I'm on about. It's very rude. But there you go. Okay, let's call it a day. Thanks, everyone.